Hello everyone, this is Mrs. Logus and I will be taking you through our last unit of first semester, Unit 6.0, which is about the law of sines and cosines, which is the last trigonometry unit we'll be doing this year. So first, little mistake that I made when I made this packet, I have Unit 6.1 law of lines. That is just blatantly wrong. It should be law of sines and applications. So please, just like it says up here, please change that on your notes. Accidental typo. So before we get into where the law of sines came from, I want to remind you from earlier this semester that if you happen to have a right triangle, remember that SOHCAHTOA still applies, meaning if this is your reference angle, this is the opposite side, this is the adjacent side, and this is the hypotenuse. And during these notes, you may notice that the good old right triangle trig does still come to help you even when we're learning law of sines in this particular video. Now, we talked about right triangles briefly, but there's a new word called an oblique triangle. Some of you might be asking, what is an oblique triangle? Well, it is any triangle without a right angle. So that means you could have an acute triangle, you could have an obtuse triangle, and a lot of the time in this section, I'm going to be drawing my triangles something like this. They look a little bit obtuse, but I'm trying to make them definitely not look like a right triangle, more like an oblique one. So let's get right down to it. This right here would be considered the law of sines formula, and I think I'm going to show you where this comes from because I'm sure some of you will appreciate that it's not just me saying, oh, this is the formula because I said so. So hold on for that. What I want you to know about the law of sines is that you can compare any of the three sides. You could use just these two, sine of A over A equals sine of B over B. Based on what you had, you could also say that sine of A over A is equal to the sine of C over C. You don't need all three. You can just use the proportionality idea that the sine of A over A equals the sine of B over B, which is the same ratio as the sine of C over little c, which will, and just to explain what all those letters mean, is if I draw an oblique triangle, get this to work here. If I draw an oblique triangle, let me name that A, B, C. All of the angles are always capital letters in this section, and the smaller case letters that you see here have to do with sides. The side across from angle A could be called lowercase a. The side across from capital B could be lowercase b, and the side across from angle or capital letter C could be lowercase c, just so you know what these letters mean in terms of a triangle. And there's a couple scenarios that work for the law of sines. The first two, you might notice, involve two angles. This first situation from geometry, angle, angle, side, means you have angle, angle, side. And the second situation, also from geometry for congruent triangles, would be angle, side, angle. So you'd have angle, a side in the middle, and then another angle. Notice both of these triangles have two angles within, which is useful for the law of sines because you need, if you're going to compare A and B, for instance, you need two pairs of angles to do so. The weird case here is number 3, side, side, angle. Now, some of you also might remember from geometry that your teacher might have made a joke. If you had me as your teacher, I made a joke about how side, side, angle, if flipped backwards, has a very bad word, and you don't want to offend your teacher by putting that on your paper. So we tried to avoid that in geometry. But as we'll learn in a later section, we're going to learn about something, the law of sines, the ambiguous case. So please hold on for number 3, side, side, angle. We'll get to that more later. Now, briefly, I want to show you where this formula comes from. So if I draw a random oblique triangle, I'll label it the same, capital A, capital B, capital C. From geometry also, you might remember that if for any triangle, a height is always perpendicular. So if you wanted to draw any height in a triangle, you're allowed to do so, and altitude always exists. So with that, you have your oblique triangle, and you created 2 little right triangles. Let me label the sides that we have as well. This side would be little a because of this, and this side would be little b because of capital B here. Let me call this the first reference angle and this the second. So if I looked at this little right triangle and I thought about using this back here, SOHCAHTOA, the right triangle trig stuff. If I thought about applying that here, I could say that the sine of my angle is opposite over hypotenuse. So sine of A would be h over b. And if I looked at the second right triangle here, I could do the same thing. If this is my reference angle B, the sine of B is equal to opposite h over hypotenuse A. So some of you might notice that both of these could be set equal to h. So if I multiplied this side by b, I'd have h equaling b times the sine of A. And if I multiplied this side by A, I could get h equaling A times the sine of B. Because h is equal to both of these things, that means they have to be equal to each other. So b times the sine of A is equal to A times the sine of B. It looks like we're getting closer to where this formula comes from. One more step, really. If I wanted to get this to look like this, I would need to divide this side by A, and at the same time, I would need to divide this side by B. So here's what would happen. The B's here would cross out, the A's here would cross out, so I'd be left with sine of A over A equals sine of B over B, which is exactly one of the ratios you can get from the law of sines. So funny thing, everything really does depend on triangles, and specifically right triangle trig. So that was the reason why the law of sines exists. Now let's actually use that and apply the law of sines now. Find all the missing sides and angles of this triangle. Another way in the future you're going to see this direction is if you see just the direction solve the triangle. Let me try that again. If you just see the direction solve the triangle, it means the same thing as above, that you want to find all missing sides and angles. So if you look at this triangle so far, a lot of you might remember that in every single triangle you've seen, the degrees always add up to 180. So if you wanted to find angle A first, you would just take 180 minus 105 minus 40, and if you did that, you would get that angle A is 35 degrees. So we've already answered one of the questions for solving our triangle. We have that the measure of angle A is 35. But the question is, how do I use the law of sines to find the missing sides? We could draw an altitude, but I think that's more trouble than it's worth. So what if I wanted to find side B first? Because I put in this 35, so let's start with what we had. The law of sines, if we go back a second, the law of sines compares A to A, B to B. So if I go here, if I look at 105, the side that it goes with is 20, and it's always sine of your angle. So if you wanted to compare sides, you could say sine of 105 degrees over its opposite side of 20 equals, and then you can compare another angle to the side to see if there's anything you can find. So what if I wanted to find side B first? The angle across from B is 40 degrees. So you could say sine of 105 over 20 equals the sine of 40 degrees over B. And if you did that, some of you might recognize that when you have a fraction equal to a fraction, that is a situation where you can and definitely should cross multiply. And if you did that, you get the following equation. B times the sine of 105 equals 20 times the sine of 40 degrees. And so if you wanted to solve for B without a calculator yet, you would have to divide both sides by the sine of 105. So far, you would have that B is equal to 20 times the sine of 40 degrees all over the sine of 105. So now if you wanted to grab your calculator, like this, I think I already have it ready. Let's see. I have 20 times the sine of 40 already typed into the calculator. One thing I want you to remember is because we're dealing with degrees, if you go to mode, please make sure that your calculator is in degrees for this entire unit. So if I do 20 times the sine of 40, I would actually highly suggest putting the 20 before the sine, because it's very tempting if you didn't close this parenthesis. The calculator is tempting to say sine of 40 times 20 and put it all as the angle, and we don't want that. So if you type in 20 times the sine of 40 and press enter, 12.855, then you need to divide that answer by the sine of 105. Close parenthesis. If I do that, I get 13.309, which is exactly what I got in the past. So my B value is 13.309, and it's very common to round to 3 decimal places. I haven't completely solved the triangle yet because I still need to find sine A, or side A, but we could still use the law of sines. Because I was given 105 and 20, I'm going to stick with it. Sine of 105 over its opposite side of 20. This time, if I want to find side A, the angle across is 35. So you could say the sine of 35 degrees all over side A. Just like last time, we could say A times the sine of 105 equals 20 times the sine of 35. So if I solve for A, I would divide both sides by the sine of 105. And I would get that A is equal to 20 times the sine of 35 degrees, all divided by the sine of 105 degrees. And if I plug that into my calculator directly, I would get that A equals 11.876 units. So I have completely solved the triangle because I have found every missing angle inside that I did not have originally. Now what I'd like you to do at this time is please read the word problem and try to make a diagram on your own, and I will come back with you in a few minutes with my diagram to see how we compare. So please pause now. So here was my general diagram. We had a balloon up here, we had a female and a male. The female was looking up at the balloon at 46 degrees, and the male was looking up at the balloon at 72 degrees from the ground. And they were 55 miles apart. So I drew them all as one triangle, so hopefully I could use the law of sines. So at this time, if you'd like to pause the video and copy the diagram, please do so. The second thing, though, is to ask ourselves, how can we find how far the balloon is from the male? So we want to find this distance here. And if we're going to use the law of sines, it looks like we don't have any angles directly across from sides that we have, unless we find this angle right here. If we add these two angles and subtract them from 180, we would get this is 62 degrees. So we could say that the sine of 62 degrees over 55 equals the sine of 46 degrees over x, because the 46 is across from the side that we want. So again, I'd like you to pause the video, and I want you to see if you get the same answer as me in a bit. So please pause now. All right, guys, so here's my work. Did a little cross multiplication, and I got the final answer of 44.809 feet. Please pause the video if you'd like to look at my work more closely. This next problem we are going to be skipping because we're going to be doing it as a warm-up, so please don't cross it out. But we're going to end on this third problem, and what I'd like you to do is, again, please pause the video, take a look at the diagram I've shown, and see if you can fill it in accordingly. So please pause now. So I said that this angle here is the first angle of elevation from where you started to the top of the building. Then you move 80 feet closer, and the new angle looking up is 33 degrees. And I also drew this right triangle here because a building is always, or should be, perpendicular to the ground. So we have an oblique triangle here. We have a little right triangle, and really a large right triangle if you think about it. So my goal is to find this height of the building, which is part of the right triangle. If we could find maybe this red length, we could use SOHCAHTOA in the right triangle. So what I want to call your attention to is this purple oblique triangle. If I wanted to use the law of sines, I would need something across from the 80 degrees, and it looks like we don't have enough. Until you notice that 33 in this angle have to add up to 180 because they're a straight line. So this would be 147 degrees. Then these two together, subtracted from 180, would get this third angle to be 12. So we could use the law of sines here to get this red length, and then use that to get to the right triangle. And I'll be back with my work. with the oblique triangle, then use this length in the right triangle.